Ladies and gentlemen, welcome again to PASCO Laboratories. I'm JP, and this week the P is going to stand for Paskowitz, or as we say it here at PASCO Laboratories, Paskowitz. And you're going to understand why that is shortly, because we're going to bring in our expert in materials testing to showcase something that you're going to find unbelievable as we're celebrating our engineers and Engineering Week and all of the great things that you can do both in the classroom or if you're doing hybrid or distance learning. Now, the things you're going to see today are going to be as if we were teaching materials labs, materials testing, physics, shop, any of the things that you might be doing. We're going to show it how you would do it in your classroom, but what you're actually seeing is how we can do it live, and you can share it with your students at home. And we're going to be using this nice device here, our materials testing system, and you're going to get to see some nice stuff. Now, this is live, so if you have questions today, just write in. We have Janet in our studio audience. Hello to our studio audience today. We have our studio audience, and Janet and Brett will be taking your questions. We'll pass them over, and we'll make sure we get them answered for you. And we're excited today because we're not just looking at one demonstration, but if you count today, you're going to see 7 different rapid-fire demonstrations by our own whiz kid, Michael Paskowitz. But don't tune out too early, because at the end, we've got a special FOMO promo to give you that you're really going to enjoy when you take a look at what we have to offer. But let's not get to that yet. You want to see some stuff? We want to break some stuff, and Michael's going to break it for you. Michael Paskowitz.
Hi, welcome to our presentation today. So we've got a lot of material to cover today, no pun intended. And we'll go ahead and start with our steel sample over here. So with the materials testing machine, we have our load cell down here, which is going to determine the load that's placed on our sample, which is loaded in here. We have the handle in the back, so your students will actually be able to feel a portion of the force that they're applying to the sample. And then the displacement of the sample is tracked by the motion of these lead screws here. Now, prior to the use of the equipment, you need to go through a calibration to make sure that we're tracking the displacement of the gauge length of the sample rather than any compression that you would get on any real material. Okay, so let's go ahead and get this started here. On our capstone screen here, we have a load displacement curve. Which we will start to record on here. So the first investigation here we're going to actually do is take a look at stress strain here, and I'm going to hit the record button. So when we do that, I'm going to very slowly advance the crosshead here. I'll go ahead and start that again here. And as we do that, if we're very careful, we'll go ahead and zoom in here. Okay, this doesn't seem to be cooperating here. So if we zoom in here, we can see that we're going to be expanding this, this section here. We'll go ahead and restart a new display here. Okay, so what we can have here is we have a measurement of the displacement here. And if we look at the slope here, we can see that it's roughly linear. The linear slope here represents the Young's modulus for the material. So if we think about these atoms within the material being attached to springs, if we stretch those springs and we increase the force, they behave like a Hookean law of spring, so you can see how that displacement happens. Now, if we start collecting data here again, and then we drop that back down again, we can see that we have a linear displacement here as we release the stress. Okay, we'll go ahead and start the run again here. And as we increase this here again, the distance here seems to be a little bit backwards, unfortunately. We can increase the stress here, and we can take it to an interesting point here. So it's going to be a linear displacement here until we get up to a certain point here. And then as the material is going to change its behavior as we get into plastic deformation. You can see that this has been curving here. We'll go ahead and change the orientation here. Just a moment, please. And we can see how it's displaced here from the linear section. So what we're seeing here is we're seeing a change in the behavior from elastic region where it's displacing linearly to where it's actually changing into plastic deformation. We can do that again here by releasing the sample. We'll start recording data again. And load it up again. And we'll take it up into plastic deformation here. Now, if we look carefully here at the screen, if we look carefully here at the very top here, I'm going to continue with the displacement here. And we'll go ahead and take it to failure. You're going to start to see a neck form. And where that neck formed, we had the sample fail. You could actually hear it fail as well. So what we did is we took this through the ultimate tensile strength. So for the stress strain curve, we're going to have a vertical axis here, and it goes up over a hump and then comes down. Okay. Now, one of the interesting things about this is it tells a story. Not only is it the load displacement curve or the stress strain curve that tells us a story, but also the fracture surface. One of the abilities that we have here within Capstone is we can actually capture the fracture surface. So with the steel sample, we got to hear it break here. And if we look on the left-hand side, we have it's like a cooking show. We have a pre-recorded sample that shows the surface where it's fractured. And we can see that it's bumpy and lumpy and showing a lot of energy was absorbed there. What we're going to do now is we're going to go ahead and reopen the file here, and we're going to take a look at the aluminum sample that we have on the other side here. So let's go ahead and do that. I'm going to go ahead and reopen my workbook here. Go ahead and transfer this over to the other device. Okay, so we've preloaded an aluminum sample here. Aluminum's got a little bit lower modulus of elasticity. It's a little bit squishier. So we're going to go ahead and pull on that as well. We're going to go ahead and get ready for data collection here again. And let me go ahead and move this secondary camera over here so we can see what's going to happen with our aluminum sample. Again, we're going to take a look at this and to see that during the initial deformation portion of this is going to show uniform deformation. Then we'll get neck formation where the sample is going to have non-uniform deformation, and we're going to get concentration of the stresses there. Some other experiments that you can do with this is when you are loading it in the elastic region, you can take measurements of the lateral size for the sample. And while it's under load, you can take that ratio between the lateral contraction and the axial extension and determine Poisson's ratio, which is important for relating Young's modulus to shear modulus and eventually to bulk modulus. Okay, so we're going to go ahead and go through the force elongation curve here. So we'll start data collection. And we're going to go ahead and load the sample here. And let's go ahead and reverse the direction on this again. My apologies. Okay, so let's go ahead and start the load here. So we can see that these are real samples. They take some energy and some force to get them to break. So we're going back up through the elastic region here. And keep an eye on that camera. And we're going to take a look for that non-uniform deformation here. Let's go ahead and expand this out here so you can see a little bit more carefully what's happening in the load displacement curve. You can see that arc over here. So we've actually gone into the plastic deformation region. And it's still uniform here. And then as we turn that corner, you're going to see, let's move this out of the way just briefly here. We're going to see that the load is going to start to drop as we start to form that neck region here. Go ahead and keep going here. And actually, one of the things that your students will hear is they will hear the sample fail. So if we look carefully on this other side over here, we'll go ahead and translate this over here, is that the sample has failed from this top level and gone down quite a bit. The reason that I'm on this load displacement curve here is that it shows the work or energy that's released when the sample breaks. So let's head back over to the microscope, and we can actually see how that is displayed in the fracture surface that's formed. So the aluminum sample has got a smoother surface, so there's actually less energy that's absorbed during fracture. And whether you take this to class or whether it's in lab, the students will actually be able to hear the difference in that energy that's released during the failure. Okay, the next thing that we're going to talk about here is we're going to talk about how this can be used in an industrial arts program, or maybe even in an apprenticeship program for welding. So whenever you're designing with real materials, it's not often that you're using a single piece of a single material. Oftentimes you have to use a joining technique to get these two halves together. We have a very gifted welder that did this welding here for us. So the test of the strength of a weld is what proportion of the strength of the original material you're seeing here. So if we look carefully here, let me go ahead and move my camera over here again. You can see the area that has been welded. You can see a little bit of the oxide on the outside layer where the temperature has been changed. And we're going to go ahead and load this up here. So on this, we can determine the load versus displacement curve here. We'll go ahead and start this process here in just a moment so that we can test this to failure. So using a different variety of joining techniques, we can use brazing, welding, oxyacetylene rather, or all these different techniques to see the different strengths. If your students are learning welding, they can actually test their own welds and see how good a job that they're doing. Okay, so let's go ahead and we'll start the record process here. And let's go ahead and do the load displacement curve here. We'll go ahead and zoom in a little bit here. So keep an eye on that and see how it's going to fail. And you can see that it failed at much lower level than the original sample did. So this is really critical for design engineers to understand that joints such as this aren't going to have the same strength as the original material. So those need to be taken into account for design factors or safety factors when design engineers are starting to use that. Okay, so now that we're talking about thermal processes, within an introductory physics class, you will talk about Young's modulus and how a sample will expand when you pull on it. Also within a first-year physics class, you'll talk about thermal expansion. These two concepts aren't married again back together again unless until you get to like a sophomore or junior level mechanics of materials class, where we start to talk about thermal stresses, or the stresses that can be generated by temperature differences within the sample. Okay, so let me go ahead and get this. I'm actually not going to take a picture of this one just yet. So what we're going to do on this side is we are going to actually heat the sample here. So let me go ahead and confirm that we are able to collect data on this side. And I'm going to load this up to about 4,000 pounds here. Let me go ahead and reverse the direction here, just a moment. Okay, and once we've done that, I'm going to load it up to 4,000 pounds. The reason for this, or 4,000 newtons rather, the reason I'm going to do this is that this will allow us to see the sign on the stresses that we're generating. Okay, that's preloaded. I'm going to go ahead and stop it and restart it. Now, when that happens, it will re-zero it. So we'll be able to see the positive and negative effects of this in terms of the loads that are generated. Okay, so what I'm going to do here is I'm actually going to heat the sample. One thing to be careful about is not to heat the load cell down here, so I'm going to heat this middle portion here. Let me go ahead and start data collection here so you can actually see. Yes? Oh, certainly. Thank you. Let me go ahead and move the camera over here and try to keep it out of the way so we don't get a little, oops, sorry, JP, got you on camera. We'll go ahead and do that there. So what we're going to do is we have data collection going on right now. We're going to change this to time. Okay, so we'll start off at 0, and now we're going to go ahead and heat the sample up. So as the sample heats up, it's going to get more tension on it. I'll go ahead and it's been preloaded. So you can see in here that the load on the sample is changing. So the load on the sample dropped because we had more thermal expansion, and it relieved some of the strain that was caused by the load on it. So as Newton's law is taking over here, the sample is again cooling back down, and it's putting more load onto the load cell, and we're able to record that. Okay, so that's one of the thermal effects of this. Now, temperature is also very important, especially for a different class of materials other than the metals. We're going to now talk about polymers. So on this right-hand side, let me go ahead and close this workbook down, and we're going to go ahead and open up a new one. Where we're going to investigate what happens to a polymer sample when you are deforming it. Typically with metal samples, when you deform them, about 90% of the energy goes into heat, and the other 10% goes into defects, such as point defects, line defects, dislocations. In this case, we're going to use a polymer sample because it has a lower thermal conductivity. The material behavior of this is going to be a little bit different. If you can imagine that polymers are long chains of organic molecules that are oriented for the original sample more or less randomly. But when we pull on the sample, something special is going to happen. So let's go ahead and take a look at this. Just a moment, let me capture the video here. Now, one of the things I'm going to do is I have to be careful not to contaminate my backsplash here. And we'll wait for that to get started here. Okay, so one of the things that we're going to do here is we're going to pull on this sample. Now, as I said before, when we had the polymers, they have randomly oriented chains that, as we pull on them, they'll start to align. And when that happens, they're actually going to bond together. And because of that, we're going to get heat not only from the mechanical deformation of the sample, but also from the, let me go ahead and open my workbook again here. My apologies. We're going to get production of heat because when things bond together, it's a lower energy state, and it's going to release that energy. And let me go ahead and relaunch this here. Just a moment, please. And we'll actually see that in the thermal signature. Also, when we're going through that process, the sample itself in that next region that is crystallized is going to go through a transformation. It's going to become much harder. When that happens, it means that the sample is going to actually create something called a stable neck that will allow the sample to extend quite a bit here. I'll wait for this to fire up here. Okay, let's go ahead and just generate a workbook from scratch. Just a moment, please. Okay, so one of the things that I would love to be able to do with this sample is I would love to be able to break this short little sample on this device. But one of the things that can happen with this is that the polymer chains, because it forms a stable neck region, the material strengthens, and it allows the neck to be very stable and to stay to extend over the entire length of the sample. So this short sample can't be broken by this instrument, not because of the strength that it can apply, but because it just gets too chewy. And one of the reasons that polymers are oftentimes called plastics is that, well, they have a lot of plastic deformation to them. Okay, so let's go ahead and generate the camera here. We're going to forego the data on this here. Okay, we'll come back to that now. Since we were talking about polymers, let's go ahead and talk about a little bit more of our structures here. So before I talked about how thermal expansion and Young's modulus get married together in mechanics of solids class, one of the other topics in mechanics of solids is also buckling of beams. And what we have here is we have our beam adapters that are part of the ME8244 system. So with beam buckling, well, with deformation of beams, if you apply a load in the middle, you can see what the deflection is by measuring it, or by Castigliano's theorem rather. Or if you pull on a beam, it's going to behave more like a solid piece of material, and Young's modulus is going to be dominating it. But when you load a slender member like this axially in compression, then the behavior is going to be quite a bit different. Instead, what we're going to see is we're going to see a buckling behavior. It's going to behave like an Euler column. And that type of failure mechanism is going to be dependent on the Young's modulus, but also on the area cross-section of this, or the bending moment area. OK, let me go ahead and launch a new application here. So we have this. Let me go ahead and get this fired up. My apologies for the delay. OK, so this shows the details of the fixture here and how it gets loaded here. We'll go ahead and take a look at the force versus position here. And we'll go ahead and try to capture the video here again. And we'll do there, and OK. So what we can see here is we can see the beam here. And we're going to load it up in compression. So let me go ahead and start data recording here. And as I do that, we're going to see a linear increase on the force here, as we would expect if something's behaving according to Young's modulus. But when we reach a certain critical value, we're going to see that the available force that can be supported is suddenly going to drop. And we can take a look at how it failed here on the right-hand side. One of the advantages of Capstone is you're enabled to capture not only the data, but also the video, so that you can share the data with your students, and you can play the data back at the rate where it is. You can also pair it with the video so that students can see the critical points of the video along with the data. So you can see how the beam has failed. Actually, in this configuration, it's going to fail more in torsion than actually in true bending. OK, so that covers the beam accessory here. One of the other great parts of this system is that we also have a flat coupon adapter. So for those of you that have used our stress-strain apparatus, the clamping mechanism here is going to seem very, very familiar. That allows you to test a variety of different flat samples, but also to much more easily make your own. What this can be advantageous for is if you're going to be creating samples that show notch sensitivity. So you can take your sample, put a notch in the side of it. And also you can introduce your own defects. You can drill a hole in the middle and see about stress concentrations. So there's a great variety of things that you can do with the materials testing system. If you have other questions, my primary assignment is on chat@pasco.com. So if you want to talk more about the material system, I'm more than happy to do so. Or you can contact me by support@pasco.com. Let me go ahead and turn things back over to JP here. I think he has some important things to say to you about some special offers that we have.
Thank you, Michael, and thank you, folks at home, for your patience as we have been working through 7 different demonstrations, 7 different things that you can do with these material testing systems. And hopefully you got to see just a little bit of a flavor of the things that you can do with the materials testing system in different classes and different things that you do. And hopefully now you understand why we call Paskowitz the Pasco Whiz. And anytime you reach out to us, we will put you in contact with Michael Paskowitz with any of the questions you have. Now, you might be asking yourself, like, what other things can I do with this as far as engineering is concerned? We've been talking a lot about the different aspects of our software software, and I did want you to know that within Capstone, we do have our Blockly coding capabilities so that you can take any of the things that you just watched Michael demonstrate today, or run it through Blockly coding so that maybe you could generate a program that tells you when you're approaching failure or when you hit failure just based on the data. So take any of the stuff that you saw, run it through Blockly coding, design a code for your students, let your students design a code so that they can show you they understand stress strain, so that they can understand failure a little bit better by designing the code and running that through Blockly. Just one more great engineering application that you can use here. Now, you were waiting for the FOMO, the fear of missing out. Like, what would you pay for a system like this? How much would you pay for a system like this? And if you take a look online, if you look at the different offers that are out there, a system like this costs roughly $10,000. But how much would it cost you? Well, I can't give you the exact price, but what I will tell you is that if you contact our own Isaac Martin, that's Isaac Martin, our Director of Sales, it's not going to cost you $10,000. In fact, I can guarantee to you a 50% reduction to $10,000, right? That's a pretty good number. And it's everything that you see here, not just like the machine, but everything that you've seen here for $10,000, 50%, much less than that. And if you contact Isaac Martin today, he's going to toss in the software, PASCO, software, Capstone, for free. So reach out to Isaac Martin, let him know that you watched this PASCO Live, that you want the software, that you want the materials testing system, that you want all of this, and you don't want to pay $10,000 for it. You want to pay much, much less, even more than 50% less, and he's going to give you that great opportunity to do that. And of course, if you're one of our international watchers, no problem. This is an international machine, and we're happy to get this in your hands as well. Just take a look for your international partner right here on our website. Take a look for them, reach out to them, and get your hands on one of these devices at any school or any university where you might be teaching materials. And if you miss any of our presentations, for example, the one that we talked about, Capstone or SparkView, or looking at the ways that you can do demonstrations with Blockly, take a look right here on our website for our PASCO Live events. You will find all of the ones that we've done and all of the ones that we've got scheduled in the future. And speaking of the future, next week, I understand that we're actually on vacation Thursday, so we're going to be running a live presentation Wednesday, excuse me, on Wednesday, where I'm going to be showing you the full K-12 hybrid solution. Hybrid, the full solution, the complete solution for every course, K-12, elementary, all the way through high school. We've built a package for you that you don't want to miss. We've been showing you a lot of great things over these weeks on how you can teach at a distance, and next week, I'm going to show you the packages we put together for you. So until next week, a special round of applause to Michael Paskowitz, our PASCO whiz, to our studio audience, and to all of you. We certainly thank you, and we wish you the best of luck, great teaching, and good day.